So our first more complicated integration technique that we're looking at is called integration by substitution. And this is the idea of reversing the chain rule. So what we're going to be looking at is, can we recognize that a chain rule happened as a hint, and then think about working backwards. So to start off with, let's just think of a simple chain rule. Let's say f of x was 3x squared plus 5x to the 8. Then your derivative would be a chain rule. You have 3x squared plus 5x inside x to the 8. And in our chain rule, remember, we did the derivative of the outside function, kept the inside function the same, and then multiplied by the derivative of the inside function. So our outside function is the exponent of 8. We would keep the inside the same, and then multiply by the derivative of the inside. And this idea of functions inside of other functions, composition of functions, is going to be the key for you recognizing that you have to use substitution, integration by substitution, to work backwards. One of the things that is going to be the key is to recognize in my answer, I have a function inside of another function. If I have that at any time, and the function that, right, we've done ones where the function inside is just a line, well then the chain rule is easy because it's just a number, and we can divide out the number. But when the function inside is more than a line, the derivatives get complicated because there's variables involved, not just a number. You can't just, decide to divide out by 6x plus 5. It doesn't work that way. Right, and here's one we had in our notes from before. And when you did the chain rule, this was really easy to see. I can add one to put this 5 back up as an exponent, and then this would be done. And of course now, in our unit, we'd have plus c. Well, that was another thing. If you forgot a plus c, if you forget a plus c on a quiz, I'll write it once. If you forget it more than once, and I'll circle it and take off the mark on the quiz. So again, when working backwards, the thing that we're going to look for is we're going to look and notice we see a function inside of another function. So that's the first thing that we're going to practice. We're going to take out 2 highlighters. The first highlighter in yellow, okay, we are going to try to find a function inside of another function. And then in green, we're going to see if the derivative of what we highlighted is present. So for example, in the first one, I see an x squared minus 7 inside the power of 4. So I have a function inside of another function. Then in green, I'm going to check, is the derivative of the yellow part present? What is the derivative of x squared minus 7? The derivative is 2x. Yes, it is. And this tells us that if you did the derivative, a chain rule happened. So now for integration, we are going to undo that chain rule. But sometimes it's not as easy, like this example that we did, everything worked out perfectly. All the numbers were, the 5 perfectly went into the exponent. That doesn't always happen. Sometimes there's extra numbers that cause some problems. So for this reason, we are going to develop a technique. But to start off with, we are going to just try to find, in yellow, is there a function inside of another function? So for the second one, can you notice that the 5 minus, oh, that's not good. It's close. There we go. The 5 minus 2x to the 4 is inside a square root. Okay? The third one. Do we see a function inside of another function? Yes. The sine x is inside of e. It's inside of e to the x. Third one, not third one, fourth one. The 3e to the x is inside of cos. So this is sort of the recognition skill that's going to help you with this kind of integration. An analysis of the original function and seeing if there's a function inside of another function. Okay? I'm going to leave this last one for a bit. We'll do the other 4 first, because this one's a little bit complicated. Okay. Here we have the natural log of x inside of the power of 4. Well, this one we did already. I can still highlight it again. The third one on the column on the right gets a little bit more complicated, okay? Because you're like, it's not as obvious that something is inside of another function. The inside function on this one is going to be this bottom part, because technically, I could think of this as x cubed minus 5x to the negative 1. So the fact that this is on the bottom of a fraction technically means it's inside of a function to the negative 1. And the last one on the right column, tan x is inside of sine. We're going to leave the very last one for a bit. We're going to switch to green. And it says if you recognized a function inside of another function, then see if the derivative of that function is present. So if there was a chain rule and something was inside and you did the chain rule, you kept the inside the same, and then after you had to multiply by the derivative. So if the derivative is present, then you'd be fine. So for example, what's the derivative of the natural log of x? It's 1 over x. So that is apparent in this question. And for the second one, where we have 2 things written the same, if we start on the one on the right-hand side, the derivative of negative 2x to the 4 is perfectly negative 8x cubed. But what we're going to find with the chain rule, and what you've probably noticed with math often, is things don't always work out perfectly. They have little things that are like, oh, just cause us a little bit of extra work. So what's going to happen in these questions is not only are you going to look for a function inside, you're also going to look for its derivative, but you're not as worried about all the coefficients. Like, for example, the derivative of an x to the 4 will always be an x cubed with numbers in front. And if we're not worried about the numbers in front, because those are just mental math manipulations that we need to do, then we can recognize that this one here, even though the numbers aren't perfect, is a chain rule as well. What's happened on the right-hand side is like, oh, if I want the -8 there, I'd also have to divide by -1/8, and that would work out perfect. So they're the same equation, but the one on the right, the derivative perfectly matches the one on the left. The idea of the derivative is there, just isn't perfectly matched. Next one, derivative of sine is cos, so that appears nicely there. Cos 3e to the x, the inside function 3e to the x, the derivative is 3e to the x. It matches up perfectly. The derivative of x cubed minus 5x is perfectly 3x squared minus 5. And the derivative of tangent is secant squared. So these ones are the most common ways that you're going to recognize that you're going to need to use integration by substitution to undo a chain rule, is if you can see a function inside of another function and its derivative is there. Now in the last one's interesting because the only thing inside of another function is the 2x. And that 2x is a line. You could do that normal chain rule by just dividing by 2. Okay? But in the last one, we're still going to be able to use integration by substitution because we have sine, even though it's not inside any other function. But the derivative of sine is cos. So if you see a function and its derivative is present, we'll still be able to use the chain rule. I guess, simplistically, you could think that this sine x is inside of an exponent of 1, which isn't really an inside function. But that one's going to make us think, can we use substitution as well? So substitution, ideally, you'll see a function inside of another function, and you'll see its derivative present. In the last one, we just see a function and its derivative present. We think maybe we could use the chain rule as well. So what does this look like? Okay? Take out my highlighter. We have a function inside of another function, and its derivative present. That's what we're looking for. And we're going to use a substitution where we choose a new variable. For whatever reason, the variable of choice for substitution is u. Okay? So you plug in, let u equal g of x, and then we can do some substituting up. So I'm going to show you what that looks like, and it works out really, really nicely. So here's our first example. Highlighting from before, you would look at this question, you'd say, I need to integrate, and I notice that I have this function inside of the other function, and its derivative is present. So the technique for substitution is you say, let u equal that inside function, x squared minus 7. Its derivative is easy to calculate. So you let u equal x squared minus 7, and then we take the derivative, and we use Leibniz's notation. So the derivative would be du dx equals, and the derivative is just 2x. And this is where Leibniz's notation is really nice for us, okay? And we have to like cheat a little bit. A little bit of it. Technically, there have been people that show this makes perfect sense, but not the way that I'm, like, it's a lot of complicated math to say that you can do this. But simplistically, it looks like this. If you think of this as a fraction, you could multiply both sides by dx. That's simplistic. Okay? Du dx is not a fraction. Du dx is one thing, it's a derivative. Okay? It's like, if you had this, you can't just say, oh, let me just move this one over there. No, it doesn't, you can't do that, right? These are things that normally you're not allowed to do because this is one thing. However, for integration, this works beautifully because it does the following. It lets me rewrite what I had before, integration sign. Then I had, in brackets, x squared minus 7. But now instead of writing x squared minus 7, I'm going to write u. I still have the exponent of 4. And then instead of the 2x, and instead of the dx, I'm replacing the 2x and the dx with du. And what we've succeeded in doing is changed what looked like a complicated integral to an integral that you know how to do as one of your easiest ones. And it was important, we changed to u, so it was also important to change to du to tell you that's what you're integrating. You're integrating with respect to the variable u. So now this is super easy. We add 1 to the exponent and divide, plus c. And afterwards, we can substitute back. U was x squared plus 7. Now I think this is one, if you looked at it, mental math, I think you could do it without substitution. I think you could just say, I can see that. I can undo my chain rule. Perfectly fine, right? One of the things I also suggest is once you're done, you want to see if you're right, take the derivative. The 5 would come out in front, cancel out that 5. Inside would stay the same to the power 4. Perfect. I have x squared minus 7 to the power 4. Then I'd have to multiply by my derivative of my inside function, and I would have 2x. So this is one that you could possibly do without substitution, okay? But the reason that substitution is nice is you don't have to worry about holding a whole bunch of mental math things in your head and worrying about them. You changed it to a very simple integral, which you had the rule add 1 to the exponent, divide, probably getting really good at that by now, and then could substitute back. Does yours have an exponent of 6 or an exponent of 4? 6. All right. So again, we look and we have to say, I see that ln, I'm going to code it the same way as before, I see that ln of x is inside of another function. And I notice that the derivative of ln of x, which is 1 over x, is present. So first of all, I'm looking for that inside function. And then also I'm looking, is a derivative of something else, the two things present in the same question. So then you let u equal that inside function. The derivative, and some of you will, here, I'll write out the step. but some of you will go right to here. I'm okay if you go from there to there right away. Now, when we replace things, instead of ln of x, we have u to the 6. And then instead of x to the minus 1 dx, we replace all of that with du. Simple integration. And then you can substitute back. So again, maybe this would be one, since everything works out nicely, you'd say to yourself, oh, I see this. I could have maybe done this directly. But when we get into ones like this one, where the derivative doesn't perfectly match up, like your inside function, and this is where I really like to talk about inside function, because sometimes students will want to just make u that part. It's very important that you do the entire inside function. So if I take the derivative and move the dx to the other side, I'll get negative 8x cubed dx. But I don't have the negative 8 in my equation. In my equation, if I highlight it in green here, I have the x cubed in the dx. So what we do before we do our final substitution is we divide both sides here by negative 8. And then you get x cubed dx matching up perfectly. Leaves me with 1 over the square root of u, because the yellow part gets replaced with u. And the green part, the x cubed dx, is going to get replaced by du over negative 8. Now I'm going to rewrite this. The negative 8 on the bottom is like a fraction of negative 1/8. The square root of u on the bottom is like u to the negative 1/2. So I'm just rearranging my equation here so it's more in a format that we're used to doing. Numbers in front, like the negative 1/8, they don't have any effect. They could be in front of the integral as well. So when we do this integration, we still have the negative 1/8. We are going to add 1 to the exponent and divide by our exponent plus c. If we multiply our fractions out, can you see that you're going to get negative 1/4? But the negative 8 times 1/2 will be negative 4. I'm going to substitute back in plus c. And this is where I feel like this technique of integration by substitution is really nice. Because if you tried to do this one directly, there's just so much mental math that you're trying to keep. You're like, there's a half. Oh, but it's moving to the top. That's a negative half. That negative half would come out in front, and then I'd have, and then you're lost, right? If you're trying to do this directly, there's so much going on with fractions and numbers and things happening that it's so easy to get lost in the process that the substitution just takes that out and allows you to say, all right, we're keeping track of things for you by doing this technique. And the -1/4, like I'm pretty certain everyone would have seen, yes, I'm going to have 5 minus 2x to the 4 to the positive 1/2. Because that derivative would mean the half would come out in front, subtract 1 from the exponent, -1/2. That would put my square root on the bottom in the end. Perfect. This part is okay. Then I'd have a -8x cubed come out in front. But I don't have that number, so how do I put that in? And now I'm lost with my fractions again. And I would most likely not have been able to figure out this -1/4 the first time. Right? And so because the technique works in so many nice places, even in ones that you might be able to do in your head, okay? Take a look at this one. See if you can do it in your head without substitution. Okay? Now we're going to do substitution to check if you got it right. So substitution would say, I notice that the sine x is inside of e to the x. That's what I'm going to let you use. The derivative of sine x is cos x. And that is nice because that shows up perfectly in this question. And when I substitute, I get 5e to the u du. The derivative of e to the u is e to the u, so the integral of e to the u is e to the u. Substitute back. So, did you get that when you looked at it directly? Could you have just looked at this one and said, I know that it's going to be 5e sine of the x? Maybe. Okay? The nice thing about techniques is they allow you to do something easily, sometimes without thinking. That's also the not nice thing about techniques. Because when you do things without thinking, you sometimes lose that ability to think, which is dangerous, right? I see kids in, I see kids in grade 9 solving questions like this. And if you would have asked them in grade 7, I said, what's x? They go 2 in grade 7. And in grade 9, they do this. What's x? Let me figure it out. Notice the difference from grade 7 to grade 9. The grade 7 student is thinking and goes, this isn't hard to think about. I can get it right away. It's 2. The grade 9 student has now learned a technique, right, that they can solve something, or the grade 9 student can do and get that quicker than the grade 7 student, because they have a technique that when it gets harder, they're able to do. The grade 7 students like, stop one. they're working that way. And especially if your answer ends up being a fraction, then that grade 7 student's like, that wasn't fair. You weren't supposed to put a fraction in your answer. But we notice the grade 9 student sometimes doesn't think, right? And sometimes does stupid stuff, right? Like, oh, I messed up the rule, I forgot you had to do the opposite. Well, how do you forget that you have to do the opposite? Because I just do things without thinking, and they don't make sense to me, then we run into problems. So I think with all of your integration questions that you do, once you're done, take the derivative. Check if your answer is right. Once you check your answer is right, ask yourself, could I have seen that directly? Could I have thought through this? Because the more thinking, even when we learn techniques so we don't have to think, which is an important thing to do, because as stuff gets more complicated, you have more things to think about. And if you can take some of those away and say, I can do this amount without thinking, I now only have to think on these complicated things, that's actually a good thing, right? But if we don't think about everything, all of a sudden we can't remember our techniques and they become harder. So it's a balance of always trying to think about what things are doing, looking at your techniques, and analyzing it afterwards. This is one where I really like substitution. Because if you look at this one, I don't think you'll get it. You try to do it directly, no. I think you'll miss something. Now you can look at it, try to do it directly, and then we'll do the substitution and see what happens. So this one's not as easy to see that there's an inside function, but this one, it is easy to see that I have a function in yellow here with its derivative present. The derivative of x cubed minus 5x is 3x squared minus 5. I'm like, okay, so since the derivative of that one is present, I'm going to see what happens if I let u equal the x cubed minus 5x. Then my derivative is 3x squared minus 5 dx. So I go to my substitution, and the bottom of the fraction is getting replaced with u, and everything on the top is getting replaced with du, so I'm going to just write 1 on the top and put du afterwards. Do you recognize this? Okay, because this is the one that is probably the hardest to recognize working backwards. What function has a derivative of 1 over u? Yes, natural log. Technically, with absolute value. For those of you in the IB course, does the formula book have the absolute value bars around it? I'll find out. I'm curious. So then, we got natural log of substituting back. It does. It didn't used to. Prior to 2021, they didn't. The IB course didn't require that you knew that it had to be the absolute. It's like relatively new for that. And this would be one where I would look at the answer and mental math-wise go, yeah, no, I did not see that coming. It looks so different than what we started with. So here, I think the substitution works out nicely because it's not easy to see a natural log appearing in this question. But once the substitution is there, the 1 over u pops out, then it's like, oh. Even that, right? That's the hardest one to recognize. Even that is hard at that time. Yes?
I think you mixed U with DU in the final answer.
Mixed u with du. Oh yeah, I did. I unsubstituted incorrectly. Thank you. There we go. All right, I would like you to try F and G on your own. All right, there's the first one. How did you do? Is yours missing a dx here? No, yours is good. Just mine is missing it. And there's the second. We're going to leave the sine 2x cos 2x for tomorrow. I'm going to give you the last 10 minutes to start on page 511.